Okay, Assalamualaikum and good day to all students. So we continue our lesson for STM32F103 microcontroller interfacing with ADC. So this is class 2 of ADC. So in this class, I will cover the ADC in STM32F103 and the register involved to program the ADC. STM32F103 microcontroller offers two 12-bit ADC. So each ADC is a 10-channel 12-bit ADC. Here the term 10 channels implies that there are 10 ADC pins which we can use to measure analog. The term 12-bit means that the steps in ADC is 2 to power of 12, which is 4096 steps. So we have 10 ADC pin, ADC 0 to ADC 9, and then we have 12 bit, means that we can step from 0 to 4096 steps. The value will increase from 0 to 4056 based on the value of the voltage per step, which can be calculated by the formula, and then this formula voltage step, and then we will get each step is 8.056 millivolt per each step. For STM32 analog volt value, range is between 0 to 3.3 volt. So analog STM32 is not a 5 volt, it's only 3.3 volt. ADC in STM32 can be performed in a single or continuous mode for single channel, scan through all channel, or externally triggered conversions. Okay, this is a pin out for diagram for STM32 microcontroller. So you can see ADC have 10 channels, as we can see in this green color for ADC pin. So the ADC 0 to ADC 7 is connected using PA0 to PA7, and then ADC 8 PB0, ADC 9 PB1. Okay, if you refer to this STM32 system architecture, so we can clearly see that the ADC peripheral is connected to the APB2 bus, APB2 bus peripherals. So if we recall from our earlier class, that STM30 clocks option, so APB2 can run at 72 MHz speed, which is, by the way, the maximum operating speed for STM32 series microcontroller. So as usual, when we write a program using a bare metal C programming technique, so we need to enable all the peripheral clock first. So if we use ADC peripherals in our project, so we need to enable the ADC clock. Since the ADC is connected to APB2 bus, so when we want to enable the ADC clock, so we need to enable it in the APB2 enable register. So RCC APB2 enable register. So when we refer to APB2 enable register diagrams, it is, so the ADC clock pin is at pin 9. This is a pin 9 is for ADC clock, for ADC clocks. So one important thing that we need to remember is when we use ADC 0, ADC 1 or up to ADC 7, so we need also to enable the GPIO clock, because this ADC is connected or using the GPIO 8 as we mentioned before. But if we use ADC 8 or ADC 9, so we need to enable the GPIO B, and because ADC 8 and ADC 9 is connected to GPIO B. Okay, for example, if we are using the ADC one, we can write a coding to enable the clock and GPIO clock. So this coding RCC APB2 enable register is equal to 0x 0204 in hex. And 04 because this is a 0010, so it's become 4. This is 0000 and then 0100. This 2. Okay, this 2. So the hex is 0204. So STM32 ADC is a pretty complex peripheral. It is designed to be flexible enough to accomplish a complex task. There are several registers associated with the ADC unit. At first, you may feel like getting lost in ocean of 32-bit register. However, things are not so. I'm not going to explain every bit because they are well explained in the reference manuals. Also, I'm not going to go through all the ADC register. I'm just explain the register that related to our programs. When we write the coding using ADC peripherals, there is no need to follow any specific sequence for programming the register. Just make sure you coded for the required ones correctly. Okay, let's start with the first register. That is a clock configuration register. That is a RCC CFGR, clock configuration register. So as we know that the APB2 can run at a 72 MHz speed, which is the maximum operating speed for STM32F103. So ADC peripherals can only be fed with no more than 14 MHz clock. So thus we should make sure that the ADC clock is run not more than 14 MHz clock. So to do that, we need to scale down the APB2 clock to not exceed the 14 MHz. So that is what we call the prescaler. So STM32 has a dedicated prescaler that scales down the APB2 clock to divide by 2, divide by 4, by 6, and by 8. So we have divide by 2, by 6, by 4, by 6, or by 8. So because we need the frequencies not more than 14 MHz, so we need to choose the divide by 6. Because 72 MHz by 6 is equal to 12 MHz is not exceed the 14 MHz. Okay, how to configure this prescale? So this can be done by configure the clock configuration register. This figure shown the RCC register. So bit 14 and bit 15. And this bit is to set the ADC prescaler. So if we are using these two bits, if we are using divide by 6, okay, if we are using the divide by 6, so we need to set the pin 15 and clear the pin 14. This means 1 0, pin 15, pin 14, because we use the divide by 6. Okay, to write the syntax or coding, so we just write coding RCC CFGR is equal to 0 x 8000, 8 because it's 1 0 0 0 and the other bit is 0. So 8000. Okay, before we can use the ADC peripheral, we need to know the ADC channel we want to use and also the sampling rate for each channel. The ADC conversions are done in a group, and group members can be one channel only or can be multiple channels. If you using a multiple channels, so the sequence of conversion can be done on any channel and in any order. For instance, it is possible to do the conversion in the following order: CH3, CH8, channel 2, channel 2, channel 0, channel 2, channel 2, and channel 15. Okay, within this group, ADC channels are converted on a scheduled round robin basis. So we can program which channels belong in a group and which sequence the ADC conversion is common. We can also set the sampling time for each channel separately. The sampling rate is defined as the number of output sample available per unit time and is specified as a sample per second. Okay, ADC group can be categorized as regular group or injected group. So in regular group, a given fixed group of ADC channels are regularly converted. We can convert up to 16 channels in a regular group. A regular group is similar to a coding running in the main loop. So for this class, we only focus using this group, regular group channel. So I'm not go on detail for the injected channels group. Okay, to set up the sampling rate for each channel, so we have a sampling rate and then we want to set up the sampling rate for each channel. So we need to refer to the ADC sampling time register and ADC sample time register 2, ADC SMPR2, and as shown in this figure. So this register is used to set up the sampling time for channel 0, because it SMPO0 for channel 0 up to channel 9, SMP9. So for example, if you use channel 1, so use channel 1, this is for channel SMP1, for set up a channel 1 sampling time. If you want to set up channel 1 to maximum sampling rate, and maximum sampling rate is 111, and to maximum sampling rate just set bit 3, 4 and 5 to 111, and so if take 8 bit it become 0 0 0 0 1 1 1 0 0 0, or in hex is equal to 3 8. So if you want to set up channel 1 to maximum sampling rate, so the coding is ADC SMPR2 0x0036, because this 011100036. Okay, to set up how many conversion you want to use, we need to set up in ADC SQR1 how many conversion we want. So we need to set up in ADC SQR1, so bit 20 to bit 23. Okay, bit 20 to bit 23. So if in our program we use only one channel, for example we just monitor one sensor in one channel, so the bits is equal to 0 0 0 0 is for one channel. So this value is same as a default value of this register, so the reset value, so default value is 0 0 0 0. So it means for only one conversions it is not necessary for us to set up this bits. We can just no need to write this, so because it is a default. Okay, and then if the ADC conversion are done in the group and sequence, and even though we are only using one channel, So we can setting our channel sequence using ADC SQR3, ADC regular sequence register 3. So this register to select the sequence of the channel you want to use. So ADC SQR3 is for sequence 1. We have a sequence 1 up to sequence 6. Up to sequence 6. So if you need to use more sequence, and for example you have a 10 sequence, so you need to refer to another SQR register. Okay, let's we try some example. So if you use only channel 3, right, only channel 3, okay, only one channel, channel 3, so the sequence, so we use sequence 1, so we put 3 0 0 0 1 1. So the only one sequence you have, so one sequence, channel 3, so 0 0 0 1 1. So if you use only channel 0, so we put 0 0 here, 0 0 0 0 0 0 here. But if you use two channel, that is the first channel, channel 0 and channel 3. Channel 0 is the first one to sequence, put in the first sequence, and channel 3 in the second sequence. So we put here for SQ1 0 0 0 0, for SQ2 0 0 0 1 1 is channel 3. Okay. If you use two channel, channel 3 first, and you want to channel 3 first and channel 0 in the second sequence. So you put channel 3 first, 1 1, and then 0 0 in the sequence 2. Okay. Okay, the AC can be powered on by setting the add-on bit in the ADC control register 2. So we need to power on this bit twice. And twice. So when the add-on bit is set for the first time, it wakes up the ADC from power down mode. And then the conversion start when the add-on is set for the second time. So the conversion can be stopped and the ADC put in the power down mode by reset the add-on bit. Okay. Okay, this is a ADC control register 2 register. So have 32 bit register. Okay, 24 to 31 is a reserve. So bit 0 is for add-on ADC on or off. And so if you want to using the ADC, so we need to on this bit. So make sure this bit is 1 and to enable the ADC and to start the conversions. Also for same register ADC CR2, so bit number 1 and bit number 2. Bit number 1 is used to select the conversion, whether the single conversion or continuous. For single conversion is reading one time only and then stop the conversion. If we want to continue the conversions, we need to set this bit to 1, so continuous conversion. Also for bit 2 and for CR2 is for A to D calibrations. We set this bit when we want to start the A to D calibrations. Okay, as I mentioned before, the STM32 has two groups, regular or injected. If we want to use the regular group, so we need to set bit 22 of CR2, and it will start the conversion using regular channel. So we use ADC1 CR2 0x004, because here 004 000000. We start the conversion of regular channel. Okay, last register we need to monitor is the ADC status register. Okay, bit 1 of this register is the EOC, end of conversions. So we need to monitor this bit to make sure the conversion is complete. Okay, that's all the register and its function descriptions. So now I will summarize the step to writing the coding to initialize the ADC peripheral. So this step is based on if you want to monitor ADC input only from PA1. An example, monitor ADC1, PA1 only continuous one. Okay, step number 1. So we configure the clock for ADC and GPIO. Okay? So we write according RCC APB2 enable register is equal to 0x0204. We can refer to the previous slide. So then step 2, configure the GPIO-A as analog input, and this is GPIO because we use the PA1, so we set up the PA120 for analog input. And then step 3, we change the prescale, and for ADC not exceed to 14 megahertz. Type RCC, and RCC configure register 0x8000, and then step 4, configure the sampling rate for channel 1, and we set the channel 1 to maximum sampling rate using the STM32 register, and then we select channel 1 for sequence, and ADC 1 SQR3 register, and channel 1 is 1 sequence register, and then we enable the ADC for the first time. So make sure we need to enable the ADC twice. So this is for first time, and then we put some delay, and then we enable for the second time, ADC for the second time. And then after that, we on the calibrations, right? Calibration on control register 2 register. For step 8, for this step, so we put for this step calibration, but we put 0 1 1 1 here because this is already 1, and add on this continuous, and then this is a bit for calibration, we put 1 here. So is equal to 7 here. CR2 is equal to 7 for on calibration. For step 9 to step 10, so this coding is right in the while looping and continuous. So step 9 is the set bit 22, is to set bit the bit 22 of CR2 to start the conversion on regular group. So important to note here that we are using the symbol, and we are using the symbol, we need to using the symbol OR here. I missed this symbol, so you put a symbol OR here in the syntax because we don't want to disturb other bit in the CR2 register, that is bit on continuous and calibration. So the last step is to monitor the status register of ADC. There is a bit 1 and off character. So we need to monitor this bit to make sure the conversion is complete. Okay, that is all for the class today. So see you in the next session. I will elaborate more on the coding for STM32 ADC interfacing. Okay, thank you for your watching. Bye.